Hello everyone, I am Mitali Sanwal. I am Senior Data Scientist at Saturn Cloud, and today I will be talking to you about getting started with Dask using Saturn Cloud. So before deep diving into any of the data science stuff, I want to talk to you about Formula One. So whenever there is a Formula One tournament, there is a pit stop. This pit stop lasts for 2 to 4 seconds. In fact, the shortest pit stop has been of 1.84 seconds. And in this short duration, many things happen. Tires are changed, mechanical adjustments are made, and refueling is done. How is it possible to do so many things in such a small amount of time? It is possible because there are a number of people who are working together. There is this big problem, which is pit stop, but they have divided it into small parts. And this is exactly what parallel computing is. It is dividing the problems into small parts and solving at the same time. So why do we need parallel computing in data science? Python is a friendly language. It is used by so many data scientists across the world. It is my favorite language. But Python on its own is not fast enough. So there is this lock, which is known as global interpreter lock. Now today, I won't be going into the details of what this lock is, but what happens because of this lock is that Python is not able to utilize multi-threading for CPU-intensive computations. And that is why we need some toolkits, like some of them you can see here, Dask, Spark, and Ray, and there are some more. So they help us work and optimize all our cores if we are working on a single machine, or they help us work on multiple machines. So what all can we do with parallel computing in data science? Imagine that you have a large data set, or you have like n number of files, and you are trying to load that data on your machine. What if the size of the data is more than the RAM of your machine? You will get out of memory error. This is like being memory bound. Or let's take, for example, that you have to do hyperparameter tuning, or you have to train your models. It can take so many hours. It has happened with me that I have just started training a model. I go out, grab a coffee, come back. My model is still running. So for all these scenarios, these toolkits will help us achieve scalability. They will enable us to work on multiple machines. And of all these toolkits, today I am going to talk to you about Dask. So what is Dask? Dask is a free and open source library. It is written in Python, so it's a big advantage if you are a Python user because debugging becomes really easy. So if you compare it with Spark, there are pros and cons. Spark can work on multiple languages. Dask is lightweighted as compared to Spark, but if you're a Python user, that's a great thing because Dask can integrate very nicely with the existing Python ecosystem. Dask will help you optimize all the cores, most of the cores of your local machine, or it will enable you to work on multiple machines. And the best part is that Dask is easy. So if you know how to write functions in Python, then scaling them up using Dask is not a big deal. And I will be showing you some examples around that. So let's talk about Dask networks. Dask networks is made up of three things. There is a client, there is a scheduler, and there are workers. So client is where you are writing commands. This is like a user-facing entry point. And whatever commands you have written, whatever instructions you have written for Dask, those will be passed to scheduler. Scheduler is the one which manages all the workers. It is the one which is assigning the tasks to the workers. And workers are the one who are actually doing all the computations in parallel. So there is this term Dask cluster. I might be using it moving forward. That is equivalent to schedulers and workers. Okay, so the examples which we will be seeing today, they will be having a Kaggle Formula 1 dataset. It is laptimes.csv. We have race ID, we have driver ID, we have lap, positions, and time for each lap. Okay, so I want to talk to you about user interfaces of Dask. Dask has two kinds of user interfaces. One is high level and another one is low level. So high level user interface can be thought of as a scalable version of NumPy or Pandas. So the standard interface remains same. That means that the way you are writing syntax in Pandas or NumPy, the same way you will be writing syntax in Dask data frame and arrays most of the times. Now, low-level interface. So imagine that you have already created a pipeline. Let's say that you created n number of functions in Pandas. And later you realize that you need some scalability. And you don't want to change each and everything to high-level interface. So in that case, you can just wrap it with low-level interface. Or maybe sometimes the computations are complicated enough that they cannot be done in Dask natively. In that case as well, you can use low-level interface. So now we will be deep diving into each and every user interface. The first one is Dask data frame. Dask data frame can be thought of as a bunch of Pandas data frame. So it's just like what we see here. We have a Dask data frame and it is made up of 3 Pandas data frame here. Let's check the example. So I have a single node example and I have a Dask. If you look at how I'm reading the CSV file, it is exactly the same way. There is no difference in syntax. But under the hood, things are very different. So when I'm using Pandas, it is reading each and every line, right from the first line to the last line. But when I'm working on Dask data frame, so Dask is lazy. Dask data frame is not going to read each and every line. It is going to read just enough, as much as is required. So it is going to read all the columns and data types. And that's it. Only when you explicitly tell Dask data frame to do any computations, only then it is going to read everything in parallel and do the computations. So if you see in the last line, I'm trying to find for each driver what is the mean lap time. The syntax again is same, just that in the end, I have added dot compute, which means that now I am explicitly telling Dask to do the computations. So now we come to another interface, which is Dask array. Dask array can be thought of as bunch of NumPy arrays. So if we look at the example here, we have a NumPy array or NumPy array. It's confusing for me. So we have a NumPy array, let's say, and we are converting it into a Dask array in chunks of 2 by 2. That means that we have 4 blocks here. Now, let's say I want to do some computation. Let's say I have to do dot sum here. So dot sum will be done in all these 4 blocks in parallel. And once these 4 blocks have been computed, then they will be added. So if you are going to compare it with the summation which is done in NumPy array, it is like 4 times faster, and minus the overhead, of course. So now we come to the level interface, which is Dask bags. Now, Dask bags can be thought of as a bunch of lists. But why do we need Dask bags? We already have Dask data frame. We need Dask bags because sometimes data is not structured. It is unstructured or it is semi-structured. So in all these cases, when we have to do some cleaning of data or we have to do some pre-processing of data, we can use Dask bags because they work very nicely when we have to do some function like map, filter, fold, etc. And once you have done the cleaning of data or pre-processing of data, then you can convert your clean data into flat columns, that is Dask data frames, and proceed with rest of the computations. So here is an example. I have some information of Formula One drivers here, and which is in a JSON file. And now I want to find the name of drivers whose rank is less than 10. So I read this on my Dask bag and apply filter function, map function, and do dot compute. So this was all about high-level interface. Now we come to low-level interface. The first one is Dask delayed. So revising what was low-level interface about. Imagine sometimes you have already written your code in single node. You have like bunch of functions and you don't want to convert it into a high-level interface, each and everything. In that case, you can keep your functions as it is. You can just add a Dask delete decorator around it and you will achieve scalability. Or sometimes the computations are complicated enough that they cannot be done in Dask natively. In that case as well, you can just keep your custom algorithm as it is and just wrap it around Dask delete. So, but under the hood, how does it work? So let's come back to cars here again. Imagine that you have to build a car. Now, there are two ways of building a car. First way is that someone gives you instruction 1. Let's say, put on a tire 1. You do that. Then someone gives you instruction 2. Put on a steering wheel. And you do that. So this happens the entire day, one by one, to and fro. This is how single node works, doing each and every execution one at a time. Now, there is another way of building a car. Someone gives you just the list of all the functions, that what all are the ways of building a car. You look at that phase, you create a blueprint that I will create a car with my other 9 friends, and you call your 9 friends and you build your car in the most optimized way. And this is how Dask delete works. It is not going to execute each and every function one after the other. It is just going to create a task graph. And then when you explicitly tell it to do the computation, it will utilize most of its resources and do the computation in the most optimized way. So let's check this with an example. I have 3 functions here: finding the maximum lap time, finding the minimum lap time, and range. And I print my result in variable C. So this is all in pandas. Now I am going to wrap it with Dask delete. So now when I print variable C, you will see that there is an object. It is not giving me the output. Why? Because Dask delete is lazy. It is not doing any computations right now. It is just creating a task graph. So when Dask delete look at all the functions, it realized that, hey, finding the maximum lap time and finding the minimum lap time, they're not related to each other. So I can put them in parallel. And then when you will be doing dot compute, then all the computation will be done in the most parallel way. So from there, we come to Dask features, which is like the second low-level interface. So Dask feature extends the Python's concurrent feature interface. It is alternate to Dask delete. But unlike Dask delete, it is not lazy. It is immediate. So sometimes your computations are evolving with time. They are real time, or we are using adaptive algorithms. So for all those cases, you can use Dask features. So here again, I have 3 functions and I'm calling .submit method for each of the tasks, which is getting submitted to the scheduler, and the result will be stored in the remote thread. And whenever you want to call the result, you can just do .result. Okay, now let's get back to Formula 1. So imagine that Lewis Hamilton has this ultimate aim of driving the car fast. Now he has 2 options of doing that. Either he can build a car himself and then drive fast, or he can let Mercedes build a car for him and then drive fast. He chose the second option, by the way. So just like Lewis Hamilton, data scientists also have 2 options. Either they can build the Dask clusters themselves, manage the Dask clusters themselves, Kubernetes, etc., etc. Or they can let Saturn Cloud do all the weightlifting, and they can just concentrate on building models, on making decisions, on doing some research work. So let us see that how using Saturn Cloud you can build Dask clusters easily. And by the way, you can log in on Saturn Cloud for free because we give you 64 GB of CPU instances. We also give you 3 hours of Dask along with GPUs. So once you log in at the Saturn Cloud, you will see here a number of resources. So resources are like computation environment, and each computation environment is connected to a hardware. So we have pre-built resources as well here for you. So you can, as per a requirement, log in and start working. So whenever you have to build Dask cluster, in general, it has to be associated with a resource. It can be a job, it can be a deployment, or it can be a Jupyter server. So here I'm going to associate a resource, a Dask cluster with a Jupyter server. So I click on the Jupyter server. We can choose how powerful you want your hardware to be. You click on the new Dask cluster, make some choices here, like what should be the scheduler hardware, what should be the worker size, or how many number of workers you want. And that's it. You click on create, you start your Jupyter server and Dask cluster. And there you go. You come to a very familiar interface of Jupyter Labs. So all you need to do here is that you need to associate your Saturn cluster class with Dask. And you don't need to pass any arguments because Dask cluster is already ready for you. So here you will see some information. I have a link to the Dask dashboard here. What is the total memory size? What are the number of workers here? So speaking about Dask dashboards, they are very useful when you want to know how is the state of your workers. If you have any questions like, is my worker working optimally or not? Or do I need to make any changes to or configure it? Then you can just look at the Dask dashboard. So this is how it looks. And on top, you can see that there is a task stream. So each row in the task stream, that is a thread. And each rectangle that you see there, it is a task. And each task is represented by a color. And that same color is represented even in the progress bar that you see here at the bottom. So the gray part here is telling you that task is ready. The solid color is telling you that task is inside the memory. And the light part, which you see, it is telling you that the task has been released from the memory. We have task processing as well, which is telling you how many tasks are there in the workers. And byte stored is telling you that how much memory is being utilized by each of the workers. So 6.13 GB means that this is the total memory used by all the workers here. Okay, so now let's see some of the examples which will tell us how powerful Dask is. The first one is hyperparameter tuning. So hyperparameter tuning in general in single node can take a couple of hours. I have two codes here. One is single node and another one is Dask. So I'm doing hyperparameter tuning here using GridSearch-CV. If you look at the syntax, it is all same. There is no much difference in the syntax. But if you look at the results, there is a big difference. So when using single node, it took 3 hours to finish hyperparameter tuning. But when you are using 3 workers in Dask, it is taking almost an hour. Then I increase my worker size to 10. It is taking just 20 minutes. And then I increase my worker size to 20 and it is taking just 11 minutes. So, and you can even make your hardware more powerful and it can be done even in few seconds. So now we know that Dask is fast. Can it be faster? Yes, it can be faster if you are going to integrate Rapids and Dask. So Rapids is a suite of open source libraries. It is utilized by data scientists for GPUs in their machine learning pipelines. So whenever you are doing your computation with Rapids, then the computations are done in GPU. So let's take an example here. Let's say you are using Pandas. Then the computations are done on CPU. So Rapids has libraries whose API literally mirrors the API of single node libraries. For example, there is this library which is known as CUDF. It does its computations on GPU. and it is very parallel to Pandas. So if you look at the syntax, it will be all same. But under the hood, things are different. Pandas is running on CPUs, but CUDF is running on GPUs. So when we integrate Rapids and Dask, we are not only scaling up, we are also scaling out. So let's say that you have a Dask data frame. So Dask data frame on its own is made up of bunch of Pandas data frame. But when you have integrated Rapids and Dask, then Dask data frame is made up of bunch of CUDF data frame. I would recommend you to check this link. It has some very interesting scenarios around it. Okay, so now this is the second last slide. I know everyone is tired here. So PyTorch is used for deep learning. When you integrate Dask and PyTorch, so we have this library, which is Dask PyTorch TDP. This will enable you to work across multiple workers. So you can train a single model across multiple workers. And if you want, you can train multiple workers as well in parallel on Dask. And this again is a very interesting blog, speeding up neural network training with multiple GPUs and Dask. I would recommend that you check this. Okay, so wrapping up, what all did we learn today? Dask can scale up our machine learning and data science workflows. It is a very familiar interface. So the high-level interface are just like the scalable version of NumPy or Pandas. If you have a custom algorithm and you don't want to change them to high-level interface, you can just use something like a Dask decorator. And because Dask is written in Python, so it can integrate very nicely with the software projects like PyTorch or Rapids. So that is all from my side.